Okay, great. Hi, everyone. Welcome to another online causal inference seminar. So today we have a special guest. So Sara Magliacane, one of our hosts, and Phillip Lippe from University of Amsterdam will be presenting together on their project called BISCUIT, Causal Representation Learning from Binary Interactions. So we look forward to seeing this talk. And afterwards, we'll have a discussion from Sébastien Lachapelle from Samsung Sail. And so we'll look forward to that as well. Today, the questions will be handled by Ying. So I'll just quickly let her explain how that is done.
Thank you, Emma. So as usual, please submit your questions through the Q&A section. You can click the button at the bottom of the Zoom window and type in your questions. I'll probably bring some clarification questions during the talk and leave bigger ones as Sara and Phillip pause, probably. And please do submit questions as soon as you have them. Don't wait for us to ask you to submit questions. And basically, that's it. Sara, feel free to take over.
Okay, thank you very much. Let me try to share the screen. Okay. Yeah, so we're here. Okay, so first, I guess I should thank the organizers for inviting us. Can you hear us? Everything's good?
Yes, yes.
Okay, great. So we decided to split our talk in two parts. So I'll do the first part. So I'll shortly introduce a bit of the context of BISCUIT. So I'll talk about causal representation learning in temporal settings. And then later, Phillip will do the second part, and he will be talking about BISCUIT. So I'll start a bit with the motivation on causal representation learning in temporal settings. So the temporal settings we're considering are like settings in which we have an environment, and we do actions in this environment, and we have a sequence of observations in time, and we also have some actions. And so you can imagine that this is a natural setting for learning from interventions, because we often observe the before state, an action, and the after state. So this leans very well to learning from interventions. So some examples of these settings are settings with sequential decision-making, for example, reinforcement learning, planning, a lot of different tasks in robotics. And you can imagine that in all of these settings, it would be beneficial to have a causal model that we want to use to choose the best actions. And so sometimes in these settings, we have as input, so the observations we have of the environment, images or sequences of images. And so our first task will be to actually extract causal variables or causal features from images in an unsupervised way. So for example, we want to learn the position of an object, the state of an object from an image directly. And so this is something that causal representation learning, or CRL, does. So first, I'll take a bit of a step back just to introduce some of the terminology and notation. So I'll talk about the more classic way to represent causality in temporal settings. So these are dynamic Bayesian networks, or DBNs. So this is an extension of Bayesian networks to temporal settings. And you can also see them as a type of template graphs. So a template is a template of a graph that repeats across instances. So in this case, it repeats across pairs of time steps. So some of the common assumptions for dynamic Bayesian networks are the one Markov assumption, which says that the variables at time step t, so let's say the present, can only be caused at most by variables at time step t-1, so just one time step back. So this is the one Markov assumption. Another typical assumption in dynamic Bayesian networks is stationarity, which means that the transition model, or in other words, the edges between the variables from time step t-1 to time step t, so these edges repeat across every possible pair of adjacent time steps. And then we have another assumption that I will use for most of the talk, except for a few slides, which is that there is no instantaneous effects. So there are no edges between the variables at the same time step. So this is an example of a dynamic Bayesian network. So we have three variables, S1, S2, S3. This is time step t-1. And here we have the same variables at time step t. And so these edges here represent the causal relations. So the variable S1 at time step t-1 causes the variable S1 at time step t, S2 at time step t, and S3 at time step t, etc. So I draw this with this box here. So this is also called the template notation, because this box means that this graph here repeats for every t, and t goes from 1 to, let's say, the last time step, big T. So to give you an idea, I'm going to take this dynamic Bayesian network and unroll it in time. So let's say we have just 3 time steps, 1, 2, 3. And so this dynamic Bayesian network for these 3 time steps will look like this. And as you can see, this part here and this part here repeat. So dynamic Bayesian network is just a concise way to represent a Bayesian network in time. And this is what we'll be learning. So this is a teaser for the second part of the talk, but just to give you an idea of the setting we consider. So we have an environment. In this example, we have a kitchen environment, and we're an agent, and we're doing actions. We're just kind of pressing things, switching on things, etc. We don't know exactly what we're doing, but what we want is we want to learn from these images and the actions that we do. We want to learn a dynamic Bayesian network that represents the causal model of the environment. For example, from the image, we first want to be able to identify in which state is the microwave. Is it switched on? Is it switched off? Is the door open? Is the door not open? So here we have, for example, an egg. So we want to know if the egg is cooked, it's uncooked. We have a potato. We have some stoves which are switched on or off, etc. So from each image, in a sequence of image, we want to extract this kind of semantic or causal variables. The second part we want to do is, from these variables, we want to learn their causal relations. For example, a microwave can cook a potato if we put the potato in the microwave, etc. So we have these edges that represent causal relations that we would like to learn. And another thing we want to learn is we have an agent doing actions, and we want to be able to kind of translate these actions to effects on the causal variables. So these are the things we want to learn, just from images and actions. So just to give you a bit of an overview, there are many works that do temporal causal representation learning. So I just selected a few of those. So the first one I selected is IVIE by Kema et al., 2020. So it can be used in temporal causal representation learning, and Phillip will show you how it also performs compared to the other methods. But it's a more general setting because it's able to assume, so it's based on the assumption that there exists an auxiliary variable u, such that the latent variables, which are the causal variables we're trying to learn, are condition independent given this variable u. So this could be, for example, the previous state, a time index, a state and an action. So this lends to many interpretations, including in temporal causal representation learning. So IVIE is more general, but it has some more strict parametric assumptions. For example, the conditional exponential family prior, and also a few other assumptions that are a bit more technical. And it assumes a sufficient variability of the data. So DMS VIE by Lachapelle et al. 2022, so our discussant, relaxes some of the assumptions from IVIE, but it still has an exponential family assumption. It has a similar sufficient variability condition. So there are some requirements, and the fact that the variables should change both in time and based on an action, in a sense, sufficiently. And there are some assumptions on the types of graphs that you are able to identify fully. So you're able to completely disentangle the causal variables from the images. Just very recently, Lachapelle et al. 2024, yes, extended this work to the non-parametric case, and also showed that if some of these graphical assumptions do not hold, we're still able to get a certain identifiability, but we're not able to potentially identify each of the individual causal variables. And then I wanted to also mention this other work, Lippe by Yao et al. 2022, which leverages non-stationarity. It's non-parametric, so this is a nice property, but it also has a sufficient variability assumption across regimes or environments. And so if there is no stationarity, if we have a stationary system, it's not able to work. And so all of these methods are able to work on both settings in which we have interventions in time and settings which also have only observations. So now I'm going to focus on a set of works which only works when we have interventions. So I'm going to talk about some of our previous work, and then these works form a bit the basis on how we extended them to develop BISCUIT. So I'm going to talk about this setting, trees, so temporal intervened sequences. So this is a setting of our earlier work. In this setting, we had, similarly to before, we had a set of a sequence of images, xt plus 1, etc. So these were some kind of high-dimensional data that represented some kind of entangled measurements of the causal variables, C1, C2, etc., to CK. So then we assumed there was a dynamic Bayesian network on these variables, C1 to CK, which were unobserved, that we wanted to reconstruct. And then the idea here was that we had the axis would be potentially noisy measurements of the C variables. Another thing that we assumed, so this part here is kind of standard, is the one that most of the methods assume, but we had an extra assumption, and the extra assumption is that we also observed some intervention variables, which were a set of binary variables, I1, I2, etc. to IK, each one paired with one causal variable, and these variables represented if a causal variable was intervened or not in a specific time step. So this way, what we assume we observed, and we had also some kind of potential dependencies between these variables. And then for this setting, we developed this method we called C-trees, causal identifiability from temporal intervened sequences. And this method was based on a variation on an autoencoder setup, in which we had as inputs an image at time t, an image at time t plus 1, and a vector of intervention targets, so intervention variables. This was 1 if the first variable was intervened, and 0, for example, if the second variable was not intervened. So given these inputs, we were able to reconstruct in the latent space vector z, and then by enforcing a transition prior that was factorized based on an assignment that we learned, an assignment psi, we're able essentially to assign these latent variables to different causal factors. And so this is what we were learning. So just to give you an idea here, we assumed, so in the C-trees work, we assumed that we had multidimensional causal factors. So we wanted to be a bit more general than the standard case in which there was only one latent variable per causal factor. So here we had multiple variables per causal factor, and therefore we had to learn an assignment function, psi. And then we had some identifiability proofs. I'm just going to go relatively quickly because Phillip will explain much more in detail what happens in BISCUIT. But in C-trees, we needed 2 strong assumptions, and one is particularly strong. So we needed to assume that we are observing these intervention targets, IT. And another assumption that is somehow also related to what happens in BISCUIT, we needed to assume that each intervention variable, IIT, was not a deterministic function of a different intervention variable, IJT. So this is for the causal variable CI, and this is for the causal variable CJ. And then given some other assumptions, so these are, in a sense, assumptions on the fact that there are enough interventions, we were able to show that under some assumption, we're able to identify the causal variables up to invertible component-wise transformations. So these were the results from C-trees. Just to give you an idea, we also had an extension to instantaneous effects. So this would be the case I mentioned, in which we can now, just for this example, have causal effects from one variable to another variable in the same time steps. So here, this became a bit more complicated. So we needed some partially perfect interventions, while before we allowed for soft interventions as well. Now we had a bit more specific interventions, and we call this method IC-trees. And one of the points of IC-trees was that now we needed to estimate both the graph and the causal variables jointly. While in C-trees, a lot of the work that we did was to estimate the causal variables, and then the graph was relatively easy because we could do it a posteriori. So these were the 2 methods we have developed for interventions. And here is just kind of a summary, also to maybe lead to the discussion and the slides from Phillip. So the pros of these methods were that we had multidimensional causal variables, which allow us to have a better reconstruction and kind of a bit more realistic causal variables. We didn't have any parametric assumptions. We were able to work also with arbitrarily dense graphs, potentially also with instantaneous effects. And we had identifiability up to component-wise transformations. So slightly more than other methods, which also needed like two permutation. But, so this is the good part. But the bad part, we had several important cons. One was that we needed sufficiently diverse interventional data. But this is a bit similar to the sufficient variability assumptions of the other methods. We only work on a temporal setting, but that's also fine. But our main cons was that we needed to know the intervention targets. And our whole set of questions was, can we get rid of this assumption? And this is what led to the development of BISCUIT. So now I'll conclude here, and I'll switch to Phillip.
Perfect.
Sarah.
Thank you, Sarah. Let me share. Perfect. I think
Looks
that's
great.
visible.
Yeah.
Thank you. Yeah, thanks, Sarah, for the introduction. Also, thanks for our organizer for inviting us. So I want to pick up where we just left with Sarah to give you an overview of the temporal causal observational learning and what also motivated us to actually now come up with our recent work on BISCUIT, causal observational learning for binary interactions, which we presented last year at UAI. So the problem setup that kind of motivated us in this case is essentially what you often have in reinforcement learning. You have an agent, you have an environment, the agent can perform actions on the environment, but often what you actually want to do is you want first to learn a representation of this environment, because we rarely want to work actually on this high-dimensional representation. And one case is that this representation could be causal. So there is basically a potential use case for causal representation learning. So you're asking basically in this specific setting, how could we learn basically causal representation here? As we have seen in Sarah's talk, essentially in a temporal setting, what we want to learn is a DBN. In the case of we have some causal variables here at time t, that have then some causal connections to t+1. And essentially, we want to identify the causal variables as well as the graph. The special case that we really consider here is that essentially there's also an agent which can perform action, and we will want to use these actions to now actually learn the disentanglement of these different variables. So just as a very quick context again, there are already a lot of different temporal causal observational learning works, as we have seen in Sarah's talk, different assumptions like parametric, exponential families, or graphical assumptions. And the key part that we are basically trying here is on the one hand that we are non-parametric, we support arbitrary graphs, but crucially compared to citrus before, we basically do not observe intervention targets, but instead assume that these are basically latent and these can be described as binary interactions. What that really means with binary interactions is what we will look at next. So essentially, a binary interaction, what we refer to is that the interaction between the agent and a specific causal variable can be just described by a binary variable. So this is often also seen, for instance, as an interaction or intervention variable that you can assume can switch between two different mechanisms. So for instance, if we are at time step t, where you have, for instance, here the microwave as a state, we could have one mechanism which describes the observational case, which basically means the agent is not interacting with an object or with a causal variable here. So in that case, for instance, the state of the microwave might not change. But we then have a second mechanism that can happen, namely if an agent decides to interact or here intervene on this causal variable, which essentially in this specific case would, for instance, open the microwave or turn on the microwave or similar. So essentially, each causal variable can now be described by two mechanisms, which are basically decided by the agent, so whether it's observational or interventional. Also, another example where we, for instance, have an object where, again, if, for instance, the agent is not deciding anything, we have an observational mechanism, which in this case, again, can also keep a causal variable fixed, but still we also support stochastic variations. So for instance, in the interaction, we might have that the action of the agent is to pick up the plate, but it is stochastically sampled where we actually pick it up. So the location is a stochastic process, so therefore your mechanism is still a stochastic part. You just decide between which of these two mechanisms is actually happening. So also just to summarize, these causal variables as well can be basically continuous. So just in the specific case before, some of them might be also discrete, and they are still evolving over time. So there are also maybe other effects, like for instance, if there's another agent that could do also actions, like these can still evolve with other means. We know that there will be some actions that perform interventions on these causal variables. However, we don't actually know these which actions cause which interventions. So basically in citrus, we had these observed to know, okay, between this time step, for instance, microwave is intervened. But in this case here, we just know basically an action at location XY has been performed. And from that, we would need to also infer actually which intervention that corresponds to. And this might be also a bit more realistic in like reinforcement learning environments, where you have basically an environment which just evolves over time by itself. So basically, if you don't do anything, there's still things happening, but you still have the option to actually interact with the environment, since you probably want to solve a specific task. And this is essentially the interventional part that you can introduce. So you can basically, as an agent, interact with the variables to cause these interventions. As a causal graph, to become a bit more formal on this, essentially what we consider is that we have a set of causal variables up here, so essentially C1 to CK, that evolve over time. So essentially here we have a temporal causal relations that go from t-1 to t, or potentially more time steps, depending on how many we might want. Then these causal variables are basically observed in an image or an observation X. So each time step, we now have observation, which is an injective function of all of these causal variables. So essentially, we know that there will be the information of all of them in the observation. And then we have the regime variable down here. So essentially, the regime variable will be the interactions, for instance, the action information that the agent has performed. The crucial part that we introduce are essentially these interaction variables. So basically now, these you can consider as binary variables, which are 0, basically in case we have observational mechanisms, and 1 if essentially this action here, this RT, would cause an intervention on a specific causal variable. And just to complete basically the picture from also before, so the XTs would be here the visual observations as from the environment, and the RT is essentially whatever action information we have as the agent, especially if we choose the action to perform. It is reasonable to assume actually you have access to action information, but not basically interventional information on the lower level. So you might also ask, okay, why would it actually help to know that these things can be actually expressed as a binary variable? And this is often that we actually see that just knowing that there's actually 2 different mechanisms already help you to identify sometimes difficult cases. So one case which often is excluded in assumptions is an additive Gaussian noise setting, where you essentially have a causal variable which follows a potentially nonlinear mean function, but basically we just add some Gaussian noise with a fixed variance. This is often tricky because essentially if you would have, let's say we ignore the whole temporal setting, just if you have Gaussians, essentially in these you can rotate around if you have a same fixed variance, and model the same distribution, such that often in this case, you cannot identify the actual causal variables. But if you now know that actually in your data, you might have basically different means, so essentially your intervention changes the mean, then if you take the 2 causal variables down here in this graph of C1 and C2, these different interventions basically cause different means for these 2 variables. And if you have, for instance, a joint intervention, it would just basically map the mean to the same mean as the 2 interventional cases individually. So essentially, each of these causal variables can be described by 2 mechanisms. Basically, observational, which is here the origin for simplicity, and intervention, which is basically a shift. But if you now start to rotate this coordinate system, which is often kind of what is invariant in these Gaussian settings, you actually start to notice that when the number of means or the number of mechanisms that each of this causal variable needs is growing larger than 2. Namely that, for instance, now if I intervene on variable 1, I see that my rotated variable changes its mean. But if I would now intervene on variable 2, then it has a third mean. So it's basically not anymore describable by a binary variable. And this is kind of a key idea that we use, because essentially as you continue to rotate, the only things you can now not identify anymore are like 90-degree rotations, basically 90, 180, 270. And a 90-degree rotation is nothing else than permuting the two variables and eventually flipping with a sign. So this is nothing else than, again, the identifiability class up to permutation and up to element-wise transformations, as we have seen in Sara's talk before. Of course, like, besides just knowing that these interactions can be described by binary variables, it will be not enough to fully guarantee that we identify the variables. And the first thing we have to also assume is, for instance, that we have sufficient variability in the interactions per variable. You can consider if, for instance, we would have a single interaction, which basically switches all of these mechanisms of the causal variables to an interventional case, then there's very little actually for us to gain, because all of these causal variables change at the same time. So in the end, we wouldn't be able to actually identify these causal variables as separate. So what we also want to see, so that we can use these interactions, is essentially having a distinct interaction pattern. So for instance, there are some actions which intervene on causal variable 1, but not causal variable 2. And there might be some actions that do vice versa, or for instance, that we then have a joint intervention on the two causal variables. But it's not that these two basic, or any two causal variables always go together into observational or interventional regime. In case that is, essentially you might have, again, partial identifiability, so that you can identify others, but not these two as together. The result that we also have here is actually what we also would be able to transfer from Citrus, namely that the number of interactions or diverse interactions you need scales logarithmic with the number of causal variables. So that's quite nice to have, because if you now start to scale actually to larger systems, to more complex systems, we don't require that we actually have like single node interventions on all of these different causal variables, but we support much more like some interventions can be then joined on multiple interventions, so that you have just less restrictions on like the power of an agent and what it can really influence and what it can just basically interact on together. And this also leads you to the case that actually often an agent with a random policy is already enough here. So essentially, if you just start to click around on an environment or similar, you may be able to already get enough distinct interaction pattern without knowing anything about the environment, without knowing anything about the causal variables in the first place. As a third assumption, as we also have seen in Sara's talk, it's also a rather common one in the temporal setting, namely that we don't consider instantaneous effects, and instead assume that the causal relations here can be resolved over time. So we always have the causal relations from time step t to t+1, but for simplicity, ignore now causal relations from t+1 within the time step. Also, we have seen there can exist some extensions also to that setting. And finally, again, we need to take a bit of an assumption of actually what these interactions cause, or what also these variables change over time. Since essentially what you could also assume, if the observational mechanism and the interventional mechanisms are identical, then essentially it's the same as if you wouldn't have any interaction. So you need to make sure that actually the interaction causes a change in the mechanism, so that these two mechanisms are not identical. And this is essentially two variabilities that we could find. So on the one hand, we can either assume that change or just the interaction changes the mechanism in a more complex way. So this is basically the dynamics variability, which considers that when this change is twice differentiable. And basically the common case is if you, for instance, have a Gaussian distribution but with a changing standard deviation. So if you would have a constant standard deviation, as in the additive Gaussian noise, the assumption A would, for instance, not be valid. But if you would have now a changing standard deviation, this would be valid again. But then again, actually, if you have an additive Gaussian noise setting, then we can still identify it if the time variability holds. So essentially, it means that over time, the changes that are caused by these interactions are not linearly dependent between causal variables. So essentially, not that two variables change exactly the same way. So essentially change the mean in the exact same way all the time, since then you might not be able to disentangle these two up to linear dependency. So essentially, if one of these two variability holds, with that, essentially, we can complete our assumption list. So we have these binary variables for interactions. We have distinct interaction patterns. We have causal relations that can be resolved over time. And finally, the variability. And under that, we can show that we can identify these causal variables up to permutation and element-wise transformations. So again, like the classical case that you might be interested in at the end. Of course, this is basically all in theory, so it's always good to have this theoretical backing in terms of what we can really achieve. But then, of course, there's also the second part, which is of interest. Can we actually implement these identifiability results in practice, and can we build a learning algorithm that can now identify it on, for instance, practical environments? And this is essentially what we will now look at. So as a reminder, first of all, essentially, we will try to also re-implement this causal model in our architecture. Essentially, we will have as inputs the observations here as like XT, our images, and our agent information, basically the action information. And what we will want to learn is a latent space. So essentially, we want to encode these images into latent space in which we can then identify these different causal variables. And again, we will then try to make use of this idea of binary interaction variables to actually guide this identification process. So we start very simple in terms of having these, for simplicity here, I show two time steps. So essentially a time step t-1 and t. And we first start with basically applying an encoder. So this could be any possible architecture, which basically reduces our high dimensional state to a much lower dimensional state. For instance, a single vector with something like 32 latent dimensions or similar. On this, we essentially create a prior. So this is essentially a VAE, a variational autoencoder, which reduces our input to a small dimension. And on this, we define a distribution, which we will then look at soon. Basically, this will be our key part on actually making this identification possible. Of course, we also need to make sure that this latent code still contains all information of our observations. So we are not losing any causal variables. And for that, we do build a decoder to also reconstruct so this classical VAE objective. And to integrate the action, essentially what we will have is that we add the action and a previous time step into a small MLP or basically also other architectures as we would need to. And we want that this model or this small neural network will predict then binary variables. So these are these binary interaction variables between the agent and the individual latent variables. And as these latent variables are supposed to be identifying different causal variables, essentially we will also correspondingly identify these interactions or interventions on the individual variables. So in terms of like a loss function, to do it again a bit more formally, we will have our encoder, which is shown here as a distribution or conditional distribution of a latent z, given x, our observation. We have our decoder, which essentially tries to invert it, so tries to predict x given z. And we have here our prior, which essentially is now over time. So we try to predict the next time step given the previous one and our actions that our agent has performed. And this objective is essentially the classical VAE objective of having a reconstruction. So the first part essentially ensures that all information is in the latent space. And the second part is the more interesting one of the prior modeling. So here we now try to actually enforce that our model or our latents follow a certain distribution, namely the prior, essentially, which follows over time. In this prior distribution, we can now choose to follow exactly what we had in our causal setup. So essentially what we want is that this distribution over our latents factorizes essentially for all of them. So we can just write it as a product over each individual latent variable, given the previous time step, and now essentially a function which takes as input the agent information, the previous time step, and essentially outputs a binary variable. So this is indeed this binary interaction variable, which we now try to predict. Of course, here also to note is when this binary function is still unsupervised. So we still have to do it unsupervised without really labels of saying this is an intervention or not. So therefore, we actually need to make an objective that we can also take gradients basically straight or end-to-end, meaning that we want to have it fully differentiably. And this is a bit more of a tricky part to set it up in an optimization setting, since it's if you just, for instance, predict a discrete variable, you will not be able to nicely propagate gradients back. So instead, what we found to work best is a continuous relaxation. So essentially, instead of predicting directly discrete variables or 0 or 1, we instead predict continuous variables. So essentially, this is like a tan-h function, which predicts a continuous spectrum between -1 and 1. And just over time of a training, we essentially start to enforce more and more that this becomes like a step function. So essentially, we decrease our temperature, which essentially makes the tan-h stronger and stronger until you have this classical step function and essentially become discrete. And that just helps because the tan-h is nicely differentiable. So the model can easily start learning in the beginning. And over time, we can really try to enforce our constraint of having this discrete step function. So if that's all in place, we also tested it on various environments to show basically where also this algorithm might be applicable and how well it might also scale to more complex environments. So essentially, first consider a synthetic environment, very simple to essentially just validate our assumptions, see basically what works and how it works comparatively to previous works. And then two more settings that might be more fitting, also in terms of realistic settings to our theoretical setting, namely causal world, where you have a tri-finger, which can, for instance, do random interactions with different objects in its arena, and in an embodied AI setting, which is here the I4 simulator, where, for instance, an agent can also perform different actions with different objects in an environment. So let's first start with a synthetic environment. So essentially here we just create random causal graphs, which we then basically map in a nonlinear fashion to an image, and essentially try to then revert this process with different methods. So many of them you have already seen in Sara's talk. So we compared it to IVE, Lippe, and DMS from Sebastian. And in these settings, for instance, of course, we also checked that, for instance, our assumptions hold, because we also use here additive Gaussian noise model. So the more tricky theoretical setting in these parts, but we still also ensure, for instance, sufficient interactions. And we find that as also our assumptions hold, our method performs very well. So this R2 score here basically shows how well you identify these individual causal variables. And we also find that like different number of causal variables or different number of interactions, so essentially this minimal interactions takes this log k into account. In both cases, we are still able to identify the causal variables quite well. Well, then for other methods, some assumptions might be actually broken here, such as basically their score is of course much harder now to identify these causal variables. But of course, a bit more interesting is now if you would try to apply it to a bit more realistic setting in like reinforcement learning. So we took here this environment which has a tri-finger. So essentially the agent can control each of these fingers individually by setting a certain torque on all of these motors and essentially accelerate the fingers around. But we use a random policy. So essentially you can see here the fingers are just doing random things around. And the action information that we give our model is essentially these 9-dimensional motor angle information that the agent basically tries to do as an action. And then from these observations here on the right, we essentially see that if we plug it into our setup, that BISCUIT is still able to identify these causal variables quite accurately. So essentially, we are able to disentangle, for instance, the object as the cube, the background, the different colors of the fingers, and so on. So essentially, that is just also a proof of concept that as you scale up, for instance, the observation function, it still works actually quite well. Another interesting thing in such environments is also now that we can validate actually what interaction variables have we learned, because we explicitly learn these interactions or intervention settings. And of course, in the simulators, because that's also a simulator environment, we can observe or basically record the ground truth interactions. And if we compare that, we actually find that we have a very accurate correlation between essentially what we identify as an action versus what our model predicted. And essentially where this is a bit less accurate is in the specific finger to cube interactions. So you can imagine that essentially it's actually quite difficult from an image to say for 100% whether the finger will hit with this specific action in the cube in the next time frame or not. So that's why we actually found that the model is a bit more uncertain there, but then other interactions which are more static were then easier to identify. And the final setting that I wanted to highlight is essentially this embodied AI environment. So there are basically various different causal variables or also objects around. So we, for instance, here have 10 different causal variables of like toaster being turned on or off, or for instance, the egg position, whether it's cooked, and so on. And the actions here are simply represented by the X, Y coordinates of an agent clicking. So all we get is just like, for instance, action on pixel 510, from which we would have to then infer that actually this corresponds to, for instance, the cabinet, and this corresponds to opening the cabinet, and so on. And again, like in these numbers, we find that it actually works quite well. But what is then also more interesting is if you start to, for instance, now visualize these different interaction variables, we actually find that we quite accurately segment these different objects. So you can also use it now for different tasks, for instance, to know if I would now want to open the microwave, what action would I, for instance, have to do, and so on. And as a last one, to also, for instance, further to validate what can we do with these causal variables is essentially that we can now try to generate new compositions of causal variables. So for instance, if you have given an input image 1, and you for instance say, okay, what would this image look like if we set the cabinet to open, if we turn on the microwave? We could take another image where these two causal variables have a specific value, encode them into a latent space, and since we identified basic causal variables, just choose the corresponding latent dimensions of these two images. So essentially take the cabinet and the microwave from image 2, add it to our image 1, and decode. And then you essentially see that we're actually able to manipulate now these images while keeping all of our other causal variables fixed. So you, for instance, here, if we have image 1 and we want to open the microwave, we can encode image 2 where all of the other causal variables differ. And just changing that latent variable gives you actually now an output where just the microwave changed. And we can also actually generate now settings which are not done before in our training data set in the simulator. So for instance, here we usually have observed that as soon as the egg is in the pan and we turn on the stove, it directly gets cooked. But since in this compositional generation, we basically fix all causal variables besides the ones that we take from another image, we can, for instance, force the latent representation to say that the egg is uncooked, but we can turn on the stove. So since we do not propagate here the causal relation, so we essentially intervene on everything, like the graph is basically empty, we can still decode the new setting and see that we actually generalize, also the decoder generalizes actually to that setting while we haven't seen it really in the training data set. So this might be also helpful to now imagine, for instance, new setups that you haven't seen during the training. And also if you want to test it out, basically we also build a bit of a demo to also play around or to get more insights of what might be going well with a model and where it starts to actually break down. So with that, let me just conclude. Essentially, this method of BISCUIT we have used to identify causal variables in such interactive environments where you have an agent. And the key assumption we took here is essentially that the interaction between the agent and the causal variables is nothing else than switching a mechanism from observational to interventional. So meaning that we have here a binary variable, essentially. And we found that it's quite applicable to various environments that could be robotics, embodied AI, or reinforcement learning. And we could also use then such algorithms to identify which actions actually perform certain interventions down there. With that, let me also thank our collaborators with which we wrote this paper, and also finish then on some references. Thank you.
Thanks so much, Philip. Okay, great. So there were a few questions in the Q&A, and you and Sarah answered all of them. We don't have any open questions for now, so maybe we should switch to the discussion. And then you'll have a chance to discuss with Sebastian and maybe some other questions if they come up. If you still have questions, please feel free to ask them in the Q&A. And yeah, Sebastian, feel free to go ahead.
Right. Yeah, thank you for the presentation, Sarah and Philip. So my name is Sébastien Lachapelle. I will be the discussant for this session. So I prepared 3 questions. We can cover all of them or not. It's really up to you. Just pick and choose. Also, I should say I have a cold right now, so excuse me in advance if I have to sneeze. But yeah, okay. So the first question is the following. So basically, I think it's clear right now that learning this entangled representation is like a good thing from an interpretability point of view, right? So I think you showed it nicely with your with your application to sort of robotic and like the tri-finger data set. You can really have like a nice view of like what these different latent variables mean, basically. I think an interesting question for future work is to see if this entanglement or causal representation learning can have some advantage for downstream performance. So for instance, in reinforcement learning. So for instance, do you have like some ideas of how these kinds of ideas could be beneficial really in terms of performance, maybe in planning, maybe to learn faster with sparse reward? I don't know. So this is something that I'm currently thinking about. So I'd like to have maybe your thoughts on that. Maybe I can just like review the questions and you can answer after as you prefer. So yeah, I think another point is that so in the last years, I think we sort of like the community in causal representation learning sort of convince ourselves that like learning these causal representation is possible, right? We have like theoretical result now that shows this is possible. I think a few years ago it was not even clear that this was like something possible in theory. I think an important direction is to sort of move these theoretical results to applied settings, and I think that's what BISCUIT is doing. So I think it's very, very nice work. And you know, I'm just wondering, like, do you have like you know, useful engineering tricks that you'd like to share with us, or maybe discuss you know, some kind of mismatch between the theory that we have and the data that we should apply these methods on? So again, this is a bit open. You can pick and choose. And yeah, also the last question is more next step, right? So so what is missing to bring these approaches to more ambitious applications, like in autonomous driving, for instance? Is it a matter of having more realistic theory? Is it a matter of, you know, having more engineers working on this project on this direction? So yeah, I'll just leave it there, and up to you to like choose something in there.
Well, thanks so much, Seb. They're really great questions. Let me maybe try to just go from top to bottom, and Sarah, feel free to also chime in here. So in terms of downstream performance, one thing that I also really see is that since you have these causal variables separated, for instance, if you now have a certain task, which has also, for instance, a reward, you can first of all find the causal variables that are related to your certain rewards. So for instance, in the kitchen environment, if you're interested in cooking the egg, you might not be interested in now opening the cabinet 10 times because you know it will have no impact actually on the other causal variables and your reward in the end. So this can be used for for, on one hand, to reduce basically your search space, but on the other hand, also hopefully to be a bit more robust. So now if, for instance, some mechanisms change that actually have nothing to do with your specific task, then you might also actually can ignore it, because in the end, basically, you know that this doesn't really impact your case, at least in a causal sense. In terms of realistic applications, so we indeed often find that the theory and the data sets or the environments we consider, there's always some mismatch. So for instance, in this embodied AI setting, also in the tri-finger, we had that some interactions are actually deterministic. So for instance, if you hit a cube in a certain velocity from a direction, it is quite accurately going exactly in that direction and might not be suddenly teleporting to anywhere else. In that case, some assumptions are always broken, but we find that often, like as long as you don't start to break actually like 20 assumptions, as long as you can actually say it's approximately still valid, we often find that these methods still generalize to the setting. In terms of engineering tricks, so one thing that we just saw also across other methods is that you really need to make sure that your whole model is nicely differentiable. So we often have some discreteness in our settings. So whether we learn a graph, whether we have to learn our binary interaction variables, as we had. So when we try to essentially just learn them as discrete variables, the model essentially failed very quickly. So the model runs into a local minima and is basically stuck there. But if you try to actually use these a bit more continuous relaxations, the model optimizes much smoother. So in that sense, there will be also a bit more engineering needed. So essentially a bit more synergy between theory, essentially setups that we can also prove, where we can actually find now settings that work, but also to have in our back of our minds, we still need to actually build a model that nicely optimizes. So there will be, I think, still a sweet spot in between, so that we actually find also theory or theoretical settings, assumptions that we know could also work in the end. And that would be one part that I think is still a bit missing for real world. But there's still also a bit more theory, I think. Like, for instance, we still have a bit of problem if our observation function is non-injective. So for instance, some causal variables happen to disappear. So for instance, an object can go out of frame and might reappear. We might have that actually also, for instance, the agent is moving around, so you change perspectives. So there are more things that we might also actually need to take into account for both theory and potentially later also engineering.
Okay.
Yeah, thank you for sharing this. So also, so from like a more maybe engineering point of view, I think that there might be some kind of tension between ease of optimization and identifiability. I think there are a few works in deep learning showing that over parameterization helps you for in terms of optimization, makes somehow the optimization problem easier. And I think there might be some kind of tension there, where when we are making the model identifiable, we're sort of making it not over parameterized, right? So I think that there's maybe a tension there that will be interesting to understand in the future. So yeah. I don't really have more points. If someone wants to react to this, or...
wait a second. So I also wanted to say something about the first point, and there was also a question in the Q&A, which is related to the first point. So there was a question about integrating like BISCUIT with more traditional agents for reinforcement learning to improve its causal representation in a particular environment. So in general, yes, I do agree that. So I think it's clear that this entanglement would help representation learning to generalize. And I think also representation learning, the reinforcement learning, and reinforcement learning could help also BISCUIT to learn better representation. So I think the answer is yes, that would be nice. And also I wanted to point out that what Phillip said about finding which part of the representation is useful for the reward or which part of the representation is useful for the transition. So there are some works, for example, there is this learning word models with identifiable factorization by Liu et al. From 2023, from the group of Kun Zhang and others. So in that work, they already started doing this kind of identifiability, in that case, more for blocks of variables. but they already started to use it to kind of improve reinforcement learning. So I do think the first part, it seems pretty clear that if we had the right match between the theory, the assumptions in the theory and the reinforcement learning kind of setting, and I think BISCUIT is one of the methods that is going there, and DMSVIE as well. So these kind of methods, I think, could be used with reinforcement learning. We still haven't figured out exactly how, but we're working on it. So first part. Second part, engineering tricks, that's for Philip. Completely agree with whatever he said. Third part, for the autonomous driving, sounds a bit ambitious, autonomous driving in general. So I think we're a bit far, since, as Philip kind of mentioned, we already cannot do things that disappear from the frame or different viewpoints. So it seems that autonomous driving may be out of the reach for both the theory and the engineering for now. So I think we still need to do a bit more work. But, we can never say never, right? So, okay. Anything else you guys want to add?
Maybe just shortly to also Sebastian's point on over-parameterization. That's indeed basically also what we found. Like most of these models or results that we showed are also for over-parameterized models, and also for basically there are some papers on partial identifiability, and I think these connect very nicely to this over-parameterized idea, because you can basically add more dimensions. So essentially, some variables might not be or distant or identified in a single latent variable, but into multiple. And I think like this direction might be also nice to really settle, for instance, that we can also theoretically over-parameterize and work well in like settings where deep learning actually also works well.
I don't have more discussion points. If someone wants to chime in and ask more questions.
Right. If there's no more questions, I think we wrap up. So yeah, thank you all for coming and giving your talks and discussing. I think, yeah, seems like that's it. Sebastian, could you please stop sharing your screen? All right. Oh, there is actually a new question in, I guess, the Q&A. I guess if Sarah, Philip, you have a few more minutes. Feel free.
So the question was, what would be the biggest challenge integrating BISCUIT with reinforcement learning? What do you want to say, Philip?
Well, I think on the one hand, it's also to find now a nice environment where we can actually also have a nice task, which makes sense. So for instance, in the embodied AI environment, there's actually not many tasks that require you of like a deep causal understanding. So these environments often have like relocate or find the apple, for instance, in an environment, which is not really where we aim for causal observation. And of course, it's also always a bit tricky find environments where your assumptions really hold. So often we have like deterministic relations, we are a bit limited. So we're still trying to actually find the perfect setting of this reinforcement learning environment where we also know like BISCUIT and the L sides really make sense here.
Sounds good.
Perfect. Okay, great. All right, I'll move on to. All right, there we go. Very nice. Okay. Yes, just wanted to once again thank our speakers, specifically Philip and Sarah, for giving this very nice joint talk, and Sebastian for discussing. It's been interesting to see a different flavor to what we usually do, but it's a fun talk. And thank you also for the audience for asking interesting questions. I hope that we all see you again next week. Next week, we'll have a talk by Krikamal Mwende from CISPA. So looking forward to seeing you all there. Thank you.
Thank you.